Hello, everyone. Is the volume bright? Okay, cool. Hello, my name is Krishna, and this is my colleague Jason. We are from Airbnb, and today we are going to be talking about our data ingestion pipeline. So how did we make it reliable and scalable? What are the problems we faced? How did we go about fixing them? So Airbnb wants to offer best travel experiences to our users, and we believe that data can play a critical role in offering those experiences. So the data team in particular, our goal is to make data, Airbnb data informed. So basically we want to build all the systems and the tools to inform all the decision making based on data and insights that we have based on the data. So where do these insights come from? It comes from the events or the user activity data that we collect when the users interact with various site-facing services. So the ingestion pipeline is responsible for taking all this data and moving into the warehouse where we can perform various analysis and derive insights. So these insights typically take a form of a machine learning model, but it can take many different forms. Machine learning is a very common example. We have various products, various teams using machine learning models built on top of this data in the warehouse. For example, fraud detection. So we have a number of models to make sure that our users are protected. For example, when a user logs in, we have a model called account takeover, which analyzes whether this particular user is legit user or someone took over his account or her account and is logging in on behalf of the user. Similarly, when someone does a booking, we want to make sure that it's a legit booking and it's not a credit card fraud or anything. Similarly, machine learning models are super useful for matching users to listings. So we want to show listings that are most appropriate to the users. So the insights are useful for engaging with the users better as well. So the growth team wants to show the best listing and engage with the users, show them the best messages that make sense to them. Again, matching, we want to take into account both the user's interest as well as the host's interest. So all of them are happy. And similarly, experimentation. Experimentation is huge. We have lots of events emitted from various experiments we run, and we want to analyze that and make sure that we give feedback to the developers whether the experiment is doing well or not. And similarly, when a new experiment is launched, we want to monitor the events quickly and give feedback quickly. So if indeed something is broken, it doesn't take days to detect all these problems. So to do all of this, the data ingestion pipeline has to be super reliable and it has to scale with the business growth. So when I joined 2 years ago, and Jason joined 1.5 years ago, the ingestion pipeline wasn't reliable and we had a lot of problems. So here are some of the challenges we faced. All the data that we used to get was JSON, raw JSON without any schemas, and we had like over 800 different types of events emitted from different sources. And these events were too fragile. It was too easy to break them. And in fact, breaking events and breaking data pipelines in the warehouse was very, very common. And moreover, we didn't have proper monitoring on all the various systems that we run, so which exacerbated the problem. So the end result of all of this was there were too many outages. And many of the dashboards we had were either missing data or were not, the data quality wasn't high. So it kind of made a lot of our users, lose trust on all the data infrastructure and dashboards and all the data we had. So we wanted to fix it. Here are a couple of examples of how bad the situation was. So we used to have a whiteboard where we used to track the number of days since the last outage, and for a while it was always in single digits. And most important dashboards about bookings and user sign up, they used to be broken, which is bad. And once it so happened that because of data quality issues, the experiment analysis that we did was all wrong, and this was an actual email that a product manager sent out to his team saying, hey, don't trust the experiment results because it's not correct. So it was really, really bad. And then we started looking through this system, trying to systematically analyze why is it so bad, what can we do to make it better. So the big important lessons that we learned was, the event data ingestion has to be super reliable. But this was actually a very hard problem. So here are the specific guarantees that we wanted to build when we made our ingestion reliable. So we wanted timeliness. We wanted to make sure that the data lands on time and all the pipelines are running predictably and all the data is delivered on time. And we wanted the data to be complete, as in we wanted to make sure that all the data that is emitted from the various services land in the warehouse on time. And finally, data quality. Timeliness and completeness is not super useful if the data quality is bad. So we want to make sure that the events that are emitted are actually correct. But it turned out that solving this is an extremely challenging problem because of 3 top reasons. One, the data ingestion, the end-to-end pipeline is extremely complex because we have events emitted from Ruby services, Java services, and then we have even events emitted from the mobiles and browsers in the wild, which get into our ecosystem through this REST proxy. And then on the other hand, on the consumer side, we have various data pipelines and then data products which consume data that is in the warehouse. And in between, we have this pipeline, all the previews are sent to Kafka, then we have a system to download data off of Kafka, and then there is a system to separate out the events based on different types and put them in the right tables, and so on. So each of these systems, like Ruby services, Java services, there are like hundreds of machines and tens of different services. And there could be a number of problems. For example, there could be broken code which is emitting bad data. Processors, some of the processors could be stuck or dead. There could be buffer overflow on the network socket buffer, or the network could be congested. Nodes fail, network congestion, broker may restart, die, that disk may fill up. So there are many different failure modes here that we need to account for and make sure that the end-to-end pipeline is actually working. So this is one problem. Second problem is the rapid growth. So the user activity was growing very fast. There was more bookings and there were more users on our website. At the same time, we were hiring a lot of developers and we were adding more and more services. So new developers come in, change stuff, and since the events were already fragile, the breakages were much more. So what this meant was whatever techniques that we come up with has to be super lightweight, and it should be easy to, it should not become a bottleneck by itself. It should be really simple, easy to monitor and implement. And finally, the biggest challenge was there is no ground truth. We don't know exactly how many events were emitted across all these different services. And so because of this lack of ground truth, in the warehouse, we cannot really tell exactly how many messages were lost. And remember I mentioned no schemas and stuff like that. So we didn't know what a correct message actually looked like and what fields should be there and what should be the value of that particular field, what is right, what is wrong. So, and finally, there were big breakages are rather easy to catch, but there were always all these subtle anomalies and subtle breakages which are much harder to catch. So these 3 challenges together made this project quite complex. So we approached it in 5 different phases. So the first we looked at each individual component that I showed in this end-to-end system and made sure that we had enough introspection and monitoring and alerting on each component. So we made sure that each component is solid. And next phase, we made sure that the end-to-end pipeline is solid. And then we looked at the data correctness. So defining schemas for the data events that are emitted and then making sure that the schemas are enforced in all the right places. And finally, and fourth, we built a system for anomaly detection, which can catch not just big changes, but even subtle changes in the data. And finally, so until now, we ran all of these systems in batch mode, which ran either at daily boundaries or sometimes hourly boundaries. And we wanted to make the whole, all of these phases much more real time. So we can actually identify problems in the order of minutes. So we'll talk about these 5 different stages now. Jason will talk about the first 3, and then I'll come back and talk about the last 2.
Hey, so I'm going to talk about the approaches we've taken to make our ingestion pipeline more reliable and scalable. So as Krishna mentioned, the first thing we want to do is to make sure every component is reliable itself. We try to understand the failure mode of each component, and also we instrument with appropriate metrics. We monitor these metrics, and we alerting on the failure of this each component. So to this end, we build some instrumentation and monitoring on different levels. So the first level is the process level healthiness. So basically the liveness of the process, the CPU, the memory, and the error rate from each component. And also we count the input and output events for some of the components, so we can capture some bugs internal to these components. We also build some week over week in comparison against these events, because we want to capture some more systematic changes on the data side. So recall these distributed systems we have, so we can have failures at different components. We may have a process get stuck in the REST proxy, so we can by monitoring the healthiness of this proxy, we can detect this failure. We may also have producers have bursty traffic, overflow the buffer, or have network issues that cause message to be dropped. So this can be monitored by a proper producer side retry and failure metrics. On the other hand, we have some pipeline bug. So we may have characterize some correct event to be bad event, and also we may skip processing some event. So all this can be captured by some metrics on comparing the input and output data of some of the component. So now we have some solid monitoring on each of the component. Is it necessary? But still not, because there may be some new failure modes, and also there may be some metrics that's very sensitive to time intervals and make a lot of noises. So to this end, we need some end-to-end monitoring, and also we need some out-of-band checks on the entire pipeline to smoke the entire pipeline, also to account for new failure modes, to quantify the event loss of the whole pipeline, and to guarantee that the SLA is not missed. And more importantly, when this error happens, we have some method to narrow down where the source of this loss. So around these concerns, we have 2 approaches. One is to build some canary events. So these canary events are standalone services that sends event to at known rate. This event has some special identities inside. So when they launched into the warehouse, we can count them and make sure every canary event made through the pipeline. This approach is very simple and reliable and accurate. So basically, we can capture some of the very tricky problems in our entire pipeline. And the other way of canary events is using the DB mutations. So we know some events that have one-to-one mappings to these DB mutations, so we can use DB mutations as a ground truth for some of these events. In addition to canary events, we also need some end-to-end auditing pipeline. So we built this end-to-end pipeline for auditing. The main idea is to attach a header to each of the events when it enters the pipeline from either the REST proxy, the Java client, or the Ruby client. So inside these headers, we have host IDs, process IDs, sequence numbers, and UI IDs. And in the warehouse, we can group by the host ID and the process ID on the sequence, and we can quantify the event loss. And more importantly, we can attribute the loss to a specific host. We can also extend this idea to a multi-hop version, so we can append tier informations when the event goes to different hops, and we can attribute loss to any internal components in the pipeline. So this is one example of the audit, the event schema for the audit metadata. So we have multiple tiers, and each tier has the ID, and each tier has the value, which is the sequence number when the event goes through this tier. So put things together, we have this end-to-end pipeline, so which can detect loss, detect holes in the sequence numbers and quantify the loss. We also have canary services which send artificial events and smoke check the entire pipeline. Also, we use DB snapshots to some ground truths for some of the events which have one-to-one mappings to these DB mutations. So now we have like solid components for each component in the pipeline. Also, we have like end-to-end guarantees of the entire pipeline. But still, this is not good enough because people may send like bad data, which like have some missing field, which makes the result like useless. So recall the challenges we have. We send events in the free JSON format. So basically, if there are some code changes or like some evolutions, we may lose some of the mandatory fields in the events. So these are some of the examples due to like code refactoring or like product iteration. We lose some mandatory field, which impact our search ranking results. So to this end, we enforce the schemas to solve the most like business critical events. We choose the schema. We choose the thrift schema because it's like fits into our tech stack very well. We also build libraries for sending thrift objects from different clients, like the Java client, the Ruby client, the JavaScript, and also mobile client. We also need to define who should like create the schema. So basically, there are two sides. One is the product engineer side, which want to define or create a new schema or involve the existing schema because of iteration on the products. On the other hand, we have data scientists who consume the event, and they want to like have a consistent view of the event. So we define some simple, lightweight workflows for the development, for evolving the schemas and also bridge the gaps between the producer and the consumer schemas. We also want to make the whole flow like self-serve and as automated as possible. So basically, we build the schema registries, and this enables us to dynamically detect, discover the schemas. And also, this is very useful for services like depend on schemas, and which can pick up the new schemas during runtime. So before we choose thrift schema, we also do a lot of evaluations on this schema, different schema stack. So basically, the thrift turns out to have a very good performance in Ruby, which is our main code base. And also, it has a very easy syntax to use, and also it has a lot of language bindings. We also define some lightweight guidelines for involving a schema, like how we can change the versions when the schema involves. So these are sample code for like how we define the schema both in Ruby and Java. And these are sample code for how you're using the sending thrift events from the JavaScript side. So basically, if there's a mandatory field missing, we can capture this when we're sending the schema or we're sending the events. Also, I mentioned that there's a gap between the producer schema and the consumer schema. Producer schema may like change a lot, but we want to map it to a consumer schema in our warehouse. So our warehouse is basically based on Hive. So in the warehouse, we want to mapping the thrift binaries to like the actual Hive table schemas. So with these three steps, I will give Krishna to introduce another two phases.
Okay, so Jason talked about all the counts and week over week counts that we have to monitor the events that are coming in and also make sure that the events are themselves correct. So regular, like week over week counts comparing the differences, like we had, when we started off, we had like a fixed threshold. Anything, if we get data less than 20% today compared to last week, then alert on that. So that worked out pretty well. So that caught us a bunch of incidents. But fixed threshold has both false positives and false negatives, right? So for example, if it's a long weekend, the traffic is naturally dying down, so it'll trigger the alert, which is a false positive. And on the other hand, if, for example, say the traffic falls down, like it goes down in a specific location or a specific device, then this threshold wouldn't catch. So that's a false negative. So they were becoming more and more common and causing a bunch of incidents. So after analyzing some of them, we built an anomaly detection system which can actually catch them. So let me take you through one of that examples. So on September last year, so we implemented a new date picker. If you have used Airbnb, you know that there are date pickers on many different pages. So the new date picker was pretty awesome. It was looking very good and it was beautiful. But it had a problem. And we launched it as an experiment, 50-50 experiment. And After a few days, we realized that something is wrong, and we shut off the experiment. So it took the data scientists several days to figure out exactly what was wrong. And they did that by first looking at what is wrong. So the data said that there is a 14% drop in the searches with dates, right? So the exact impact wasn't really very clear, and then it involved a lot of guesswork. At this point, we ran a bunch of slice and dice queries. We sliced the data based on various dimensions. There was a lot of guesswork, and after some luck, we figured out, okay, so there is something wrong with some of the countries. So if you slice it by country, you see that, for example, here, Italy and Great Britain are 40% down, while the other countries are only 14% down. So something is clearly wrong. And in parallel, some other data scientist was slicing by different dimensions and then figured out the date picker is actually bad only on one page. It's actually much worse on one page. And if you combine the two insights, you see that certain countries are much worse than the other countries. And it turned out that the new JavaScript library that we were using was not doing the localization properly. So it was missing the localization translation keywords for some of the countries, and that was resulting in a JavaScript error, and the searches were doing random search instead of doing the proper search. So that was the result of the searches going down. But because it impacted only a few countries on a specific page, it didn't trigger the threshold of 20%. So as you can see, there is a lot of guesswork here, slicing and dicing, and a lot of experimentation. So then we were thinking, so these kinds of incidents were becoming more common, so how can we catch them without, not so late, but much faster and without so much manual effort? So, okay, we thought, let's automate this process. So what is actually going on? We have data on many different dimensions, and some of those dimensions are bad, right? So we could simply go and try every dimension combination, but that would be too bad because the combination of dimensions, especially with high cardinality, is going to explode. Even if we have a huge Spark cluster, it's not going to finish. So we have to be smart about drilling down on dimension combinations and picking what to drill down into in a smart way. So we built a system called Curiosity. At a high level, it does a breadth first search crawl on the OLAP cube for for all this dimension combination. So at a very high level, these are the steps it goes through. So we take all the data, we take the dimensions and the metrics for the particular data set, load it into Droid, and then we have a Spark job which goes through these 5 steps. So first it queries the time series, and it groups it at total aggregate time series by groups it by time, and then looks at the aggregate time series. And then it runs anomaly detection on that. It just looks at week over week seasonalities, spikes and dips. That's called the detector module. And after it does the aggregate, then it does group by different dimensions. So for example, if we say, okay, country and platform and say something else is the most important dimensions, it'll start group by country, and then it does something called Explorer, where it is going to compare the time series for a particular value in the group by across each other. So it's going to compare the time series for different countries. And this is how it would catch that certain countries are performing poorly compared to others. It does a comparative analysis. And once it figures out, okay, these set of countries are contributing a lot of traffic and seem off compared to the other countries, then it pins those countries' dimensions and then starts slicing and dicing in the different, in other dimensions like platform. And it keeps repeating the same process. So before it does BFS, there is a step of pruning where we check and make sure that the dimension combinations that we have in the queue are, contributing meaningful amount of traffic and are actually informative or anomalous. And then we drill down, basically go back into the queue and then pick more dimension combination, drill down, and repeat the process until the queue is exhausted. So we built this system. It's been operational for about 5-6 months, and it has already caught a lot of incidents without all the manual work. So until now, all the stuff that I talked about, we initially did them in batch mode. It used to run after the data for a particular day has landed in the warehouse, and it used to do on the daily data. Obviously, that's too slow, right? So we'll catch incidents tomorrow if something happens today. So we want to make it faster. So initially we tried hours. Now we are doing at the granularity of tens of minutes. And our goal is to get to less than 2 minutes by the end of the year. So we built a real-time ingestion system, which basically made the whole ingestion process much more real-time. I'll give a very quick overview of how it works. This is our newer ingestion pipeline. So we have the same old producers and the Kafka cluster. Instead of having MapReduce jobs for consuming data, now we have Spark streaming jobs which keep running continuously. We have 1-minute batches. And then it takes the 1-minute batch, and then it uses HBase as a state store for stateful stream processing. And at the end of every hour, we dump the snapshot of data in HBase into hourly partitions in Hive. And then, in addition to all of this, we have built connectors from Hive and Presto to connect to HBase. And then we have built views on top of them. So by connecting to a single table, you can get daily partitions, recent hourly partitions, and the current partition. And the current partition always hits the HBase, everything else hits HDFS. So we have schema registry, and so all the events that are coming in are schema thrift events. And we use the schemas in the schema registry to unpack and store them in HBase and HDFS for analysis like manual analysis or analytics. This is how it looks. There is not too much time, so I'm going to pick a few interesting things that we have learned, talk about them. So the first most important thing is how do we scale it? So to be able to scale it, we want to distribute all these events evenly across all the region servers. But at the same time, because prefix lookup and scanning for all the events is very common, we wanted to group all the events together in a given region server. So what we do is we use the event type, event name, and the unique ID in the event as the event key. We hash it into this range where region servers are assigned. We pick the start range for a particular region server and use that key as the prefix. So this prefix is used to route to a particular region server, and once it goes to the region server, it uses the entire row key. So all the events with the same name are nearby, so our queries are much faster. Another problem that we ran into is that when we have the Spark batches, which does deduping and then it writes it into HBase, we used to see a lot of jitter, and the job wasn't very smooth. It turned out it's because of the number of connections we were creating. If we have n executors and m region servers, each executor could connect to any of the region servers, so there was n times m, which was causing a lot of jitter. Sometimes when there is GC on the region server, the latency used to spike. So what we did was in the batches, the Spark streaming batches, after doing dedupe, we partition it in the same way according as that of the region servers. So by partitioning all the data that we have based on the region server's partition key, what we do is we limit the number of connections that are going from the executors into the HBase region servers. So it'll be, instead of n times m, it'll be in the order of n, which made things a lot smoother. And finally, the interesting bit, one of the interesting things that we built was the HBase and the Hive connectors, Presto and the Hive connectors. So this is how a example table definition looks, which connects to HBase. So we have the usual table name, and then in the survey properties, we specify whether it's a hourly boundary. If it is true, it's going to expose data at hourly boundaries without explicitly specifying the min and the max timestamp. If you don't do that, you can even do longer range queries by specifying the min timestamp and the max timestamp, and the queries will scan across this time range rather than hourly. And then we implemented a bunch of optimizations into the HBase storage handler where we can push down certain keys. For example, I'm interested in only event of this particular type. Then the push down key is going to limit the queries to a particular range, which is much more efficient. So the conclusion is that we started with a really hard problem of making our ingestion pipeline reliable and scalable. So data timeliness and completeness and data quality were huge important goals for us. So where we are right now is that we are able to ingest over 5 billion events every day with a loss of less than 100 events a day. And even when there is a loss, we can exactly pinpoint using all the techniques that Jason talked about, exactly which host lost the event, and within a host, which particular process was responsible for losing the event. And then, because of the schemas, all our events are correct, and the anomaly detection system is super helpful in catching not just big changes in the traffic, but even subtle changes in the traffic, which has caught a bunch of incidents much sooner than it would have otherwise. That's all. I can take questions.
Question about on the schema registry.
Yeah.
Can you explain how it is leveraged across platforms that you are distributing?
Yeah, sure. Jason, you want to take that?
So which question?
The schema registry. How do you use it in different platforms?
Sorry, what's the question? I didn't.
How do we use the schema registry in different platforms?
Oh.
Java, Ruby.
Oh, okay. So yeah, so for the schema registry, we have Java and Ruby most of the case. And we build different libraries like for JavaScript, which we will ship with the client code.
So to elaborate more, for Java we build the jars, and for Ruby we build the gems out of the schema registry, and for JavaScript, which is the browser side, and the mobiles, we build more libraries and ship them with the mobile code or with the JavaScript that is sent to the client. And so on the client side, this library, the gem, jar, or whatever JavaScript files are sent down to the client, is used to enforce the schemas upon emission. Yeah.
Do you have this anomaly detection as open source? Or?
It's going to be open source soon, and there'll be blog posts and maybe more talks.
Do you know the timelines?
I believe by the end of the year.
Did you guys consider Apache Avro over Thrift?
We did, and part of the reason was that there was quite a bit of use of Thrift already, and people were a lot more comfortable. So that was one of the reasons why we chose Thrift. And performance in our experience was a lot better in our evaluation that we had.
So you were talking about unpacking events from JSON into the, say, Hive tables, right? So it looks like you kind of map individual columns from JSON into some Hive columns. Is that so? And if that's the case, then how do you handle evolution? Like when you add a new field to JSON, what happens to Hive table schema? Do you update it every time, or is it automatic? Or
right.
how is it handled?
So we used to have a lot of JSON data. We still have quite a bit of JSON. So there are two kinds of tables. So one is the raw event is the raw JSON is exposed as a string, and that's where all the data lands, and that's one of the sources. And on top of that, you can define your schema for a particular JSON blob, right? So event name, and then that would go into a separate schema table. And there is a different pipeline that generates the schema table. And whenever there is an evolution, then you have to update that particular mapping.
Does it happen manually?
That has to be manual, yes.
So my question is around anomaly detection part. What were the factors that you considered for picking something like breadth-first search over, say, self-organizing maps, or something which is known to be kind of good for multi-dimensional values?
I am actually not the expert that built that. So, so we basically experimented with 3 different algorithms: Kalman filter, scan statistics, and snapshot explorer. On the data set that we had, it worked pretty well. But I'm not specifically sure how clustering would work. So I have to figure that out, yeah.
All right, thanks.
Two questions. One about, do you have any cases of double delivery of data? I noticed you mentioned 100 events are dropped maybe one in a day. But do you have any cases of double delivery of the same event?
We dedupe based on the UUID before we ingest anything. So duplicates are removed.
And the second one is around the detection of where an event got dropped. I think you mentioned the Canary service is basically tracking the, I guess the Canary mechanism is basically tracking the event as it goes through each tier.
Right.
But once it gets dropped, what happens? Let's say, on your third tier, the event got dropped,
right.
which, when it gets dropped, does it get logged somewhere or something?
No, so there is a sequence number to each event, right? So, for example, for each process, we have a process unique ID, and then the process keeps incrementing the sequence number. So let's say sequence number 3 was dropped, and you get 4. Now there is a hole in the sequence number, right? So then you know exactly how many were dropped. And we can group by on the host and the process ID to know which process's data was lost.
But how do you know where it was dropped? Because it's essentially a hole. You detected that there's data missing.
Right.
Now you need to know, like, it went through tier 1, 2, and 3, but got dropped at 4. How does that work?
I think we attach the host ID and the process ID in the metadata. So when we have a 3, like a hole in the sequence ID, we also know that from which host and process this hole belongs to.
So where is the data for the dropped data?
So basically, there is also something called metadata events, which emit information about these events, and they contain information about which events made it to what phases, and that helps us. Right, you're right. So basically, with just the headers, we can detect that there is a loss. We use the metadata events to correlate. We look up that particular event ID and know until what step it made it.
So every event is tracked all the way.
Yeah.
Carry a globally unique ID across, or how do you do that?
It's not global unique, but it's unique to that.
It's unique to each
host,
process
each
and
process.
host. And it's when the process starts up, it gets a unique ID.
But that would be very hard for you to correlate, like this message flows from point A to point B to point C. How do you know that message went to point C and not that point C generated a different UID?
For each hop, we have a different layer tier in
There are multiple.
So basically, it's appending the header across the tiers.
Oh, I see. So every tier that the message flows, you keep
Yes.
Appending
Yes.
it. So basically,
Yes.
if you lost the second tier, you know
Yes.
the second tier.
Yeah. Yeah.
So at the end, wherever it is, wherever it's stopped, you know how far it is.
Yeah.
Cool. What's that? So how many tiers do we have? Nodes.
How many boxes ingest 5 million
So I mean, the producer side we have like maybe hundreds of boxes, but in the Hadoop cluster again, several hundreds of machines. Yeah. Cool.
Thank you.
Thanks.